So we've looked at systems of inequalities, and I've got three more here. What we're going to do is we're going to look at how we can use these systems of inequalities to help us solve some real-world problems. We're going to call this optimization. Well, let's actually get these three inequalities graphed here on our graph. Let's see. Let's make this one the red one. So I have x greater than or equal to 2. So that would be, here's the line x equals 2. So I'd have a solid line greater than or equal to, and I would shade everything to the right. So there's x greater than or equal to 2 graphed. Let's make this one the blue one. Got a little bit of work to do here. So x minus y, so I'd minus the x from both sides. That would give me negative y less than or equal to negative x plus 8. And now I divide by negative 1, remembering to flip the inequality sign. Negative divided by negative would be a positive. 8 divided by negative would be negative 8. So dividing by negative 1 gives me a y-intercept of minus 8. 2, 3, 4, 5, 6, 7. Whoops. All the way down here. And a slope of 1. And a solid line. So like so, and greater than or equal to, I'm going to try 0, 0. Is 0 greater than or equal to 0 minus 8, which is minus 8? Yes, it is. So now we're talking this region. And then finally, the green one, y is less than or equal to 3. 1, 2, 3. Here's the line. Here's the line y equals 3. And less than would be all of this region below it. So if I'm looking for the region that satisfies all of these conditions, I'm looking at this box, or triangle here, I guess. Right here. So this would be the triangular region where these points, all of these points in this little triangle would represent values that would work in this in these inequalities. Now let's say that I had another function t, and I wanted t to equal 2x plus 5y. Now if I say so this model here, y or t equals 2x plus 5y, if I wanted to find the maximum, so the xy values that would make this answer, make t, in other words, be as big as possible, or to find the values that would make t as small as possible, out of all of these points in this area here, it turns out that the maximum and the minimums will always occur right on these corner points of these regions. So in other words, we've talked about all the points in this triangle, all of these points in here, and all the points on this line and that line and this line, all of these points, they're the ones that work in all three of these inequalities. If we wanted to take any of these points and substitute the xy value into this equation to try to make t as big and as small as possible, they will always occur at these corner points. So if we're going to try to use some inequalities and find maxes and minimums, maximum and minimums, which we call optimizations, then really the only points we're interested in locating are the corner points of our region. So let's determine what these points are here. So here's my x-axis, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then this would be 1, 2, 3. So this point, oops, slide this over a bit. So this is the point 11, 3. This would be the point 1, 2, 1, 2, 3. So this is the point 2, 3. And this is the point 2 minus 1, 2, 3, 4, 5, 6. 2 minus 6. So now if I want to find out what the maximum and the minimums are, I'm just going to evaluate each one of these things at those points. So let's try the first one up here, t. If we use the point 2, 3, here's what we would get. We'd get 2 times 2, so putting 2 in for x and putting 3 in for y would give us, 2 times 2 is 4, plus 5 times 3 is 15. So t would be 19 at this point. Let's try the next point, the point 11, 3. So t would equal 2 times x, x is now 11, plus 5 times 3. So that's 22 plus 15, which is now 37. So far this is our, and this is our smallest one. And let's try the last point here. Whoops. There we go, sorry. Let's try the last point here, 2, negative 6. So t is 2 times 2 plus 5 times negative 6, which is 4 minus 30, which is negative 26. So in other words, if we want t to be the smallest, this would be the point that would give us the minimum value for t, and this would be the point that would give us the maximum value of t. And even though all these other points in here would satisfy this inequality, none of them would give us a value bigger than 37 or a value smaller than minus 26. So let's look at more of a real-life situation here. Let's say Jack and Melinda, they have weekend jobs at a marina, and they're putting anti-fouling paint on the bottom of boats. That's some paint that goes on the bottom so that barnacles and other types of marine life don't grow to the bottom of the boat. So we know that Jack can work no more than 14 hours in a weekend. We know that Melinda, she can work no more than 18 hours in a weekend. The marina wants to hire both of them for 24 hours or less in the weekend. And we know that Jack paints one boat in 3 hours and Melinda needs 4 hours to paint one boat. So the marina has all this information. They want to maximize the number of boats painted in a weekend. So who should they hire and how long should they hire them type thing. So the first thing we want to do is we want to come up with all of our restrictions, or sometimes we call these constraints. And these will simply be inequalities. So I'm going to, actually the first thing we're going to do is going to identify some variables. So J is the number of hours Jack works. And actually I'm going to use let's use a capital J there. And then Melinda, we'll call her M. Here's the number of hours that she can work. Okay, so now we can come up with our constraints, our restrictions. So Jack can work no more than 14 hours per weekend. So my first restriction is Jack is going to be less than or equal to 14. Melinda, she can work no more than 18 hours. So she's less than or equal to 18. The marina is going to hire both of them for no more than 24 hours. So that means that Jack plus Melinda has to be less than or equal to 24. We also know that technically Jack has to be greater than or equal to 0. There's no way we can have a negative number of hours. And Melinda is also greater than or equal to 0. She's not going to work negative hours. So there's some more restrictions on our variables, or constraints we call them. And so these here we would call our constraints. They're really the restrictions or the conditions that we have to work with. And then what we want to have happen here is we want to maximize the number of boats that are painted in a weekend. Well, we know that Jack paints one boat every 3 hours and Melinda paints one one boat every 4 hours. So that means that the number of boats, let's call that B. So B is number of boats painted. If Jack is painting one every 3 hours, then if we take the number of hours that he works, which is J, and divide that by 3, that'll tell us how many boats he's painted. And Melinda, she's working M hours, and we divide that by 4 because she needs 4 hours to paint a boat. Then this little expression here would represent the number of boats that get painted in a weekend. J divided by 3 and M divided by 4. This is what we would call our objective function. And in this case, we want to maximize it. We want to make that as big as possible. So here's our objective function. And then here's really all of our inequalities. So what we're going to do is we're going to graph these. We're going to graph these constraints. And that's going to give us a region with some boundary points on it. And then we're going to take those boundary points and we're going to substitute them in here into this objective function and find out which one's going to give us the most number of boats. So let's get a graph going here. And I'm going to use one like this because I can't have any negative values for J or for M. So there's no point in doing the full 4 quadrants in our graph. And we can arbitrarily decide what we're going to put on here. I'm going to make this side M and this side J. But you could do this the other way around. This one wouldn't really matter which axes you put on which one. So I'm just going to start graphing these things. J is less than or equal to 14. Well, I might decide to go up here by 2's. And we'll do this one by 2's. Okay, so J is less than or equal to 14. So here's J. J is less than or equal to 14. Here's my 14 line. So less than or equal to 14 would represent all of these points here. And M less than or equal to 18. Let's get some different colors on here. Here's 18. This is M less than or equal to 18. So far we're looking at this box right here. This is the box that's working, where both of them are shaded. Now, we know that J is greater than or equal to 0, so we've already dealt with that because we have positive J's, and M greater than or equal to 0, we have positive M's. So far we're good with that, we're good with that, we've done that, done that. We haven't looked at this constraint yet. So let's do that. Let's isolate M. So just that's simple. That's just bringing the J over to the other side. So bringing the J over to the other side gives us negative J plus 24. So for this one, let's do this in blue. We got a y-intercept of 24. That's right there. And we have a slope of negative 1. So that's like down 1 over 1, or I could go down 2 over 2. Same thing. That's going to give me this line. There we go. So I think now we have got all of our constraints done. Yep, we just did that one. So now let's look at what we've got for a region. It looks like we've got all the way over to here. Oh, we didn't figure out which region this one was, did we? Let's try 0, 0. Putting 0 in for M, 0 in for J. Is 0 less than or equal to 24? Yes, it is. So we are looking at everything below this blue line. 0, 0 worked. So everything below this blue line is good. So our region does end up being this one right here. These are the points in here that work in all of our criteria. And then all the way along here. So it looks like we have, when we look at our region, we have 1, 2, 3, 4, 5 points. And we're going to try to maximize this thing. So let's look at all of our points. We have, let's call this point 1. Let's just start up here. So this would be the point 0, 18. We've got the point, let's do this one. Let's just go clockwise around here. This is the point 6, 18. This is the point 14, 10. This is the point 14, 0. And finally, our last point is the point 0, 0. So let's see what we get when we substitute all of these points into our objective function. So in the first one, we would get the number of boats equals j. Now our first number is j. So these first values are j, and the second values are m. X first, then y. So 0 in for j, and 18 in for m. We would get the number of boats to be 0, and then 18 divided by 4 would be 4.5. So 4.5 boats would get painted on the weekend. If we went with scenario 2, so notice in scenario 1, this would be if Jack worked 0 hours and they just basically hired Melinda for the whole thing. They get 4.5 boats painted. For the next one, we're going to put 6 hours in for Jack and 18 hours in for Melinda. Now Jack would be painting 2 boats, and Melinda is going to be painting 4.5 boats. So now we get a total of 6.5 boats painted. So this is a better situation. Looking at the scenario here, we have 14 hours for Jack, and we have 10 hours for Melissa, or Melinda, whatever her name was. Melinda, I guess. So 14 divided by 3 would be 4 and 2/3, I guess, 4.666. And this one would be 10 divided by 4 would be 2.5. So here they would get 4, 5, 6, 7, about 7.2 boats done. So 7 boats, especially if they combine forces on the last boat there. So 7 and a bit done. And in this situation, we'd have 14 divided by 3 plus 0 divided by 4, which is going to get a little more than 4 boats done. 4.666. And finally, in the last situation, well, obviously this isn't going to be very productive. If we hire them both for 0 hours, we get 0 boats done. So this would be like our minimum situation. But obviously for the marina, we're looking for a maximum. So it looks like scenario 3 here would be the best deal. Hire Jack for 14 hours, hire Melinda for 10 hours, and the marina would get 7 boats done and a little bit of the next boat. So let's summarize how we would use linear inequalities to solve optimization problems. So to solve optimization problems, what we're going to do is, from the information given in the question, we're going to determine a set of inequalities based on the constraints. So we're going to come up with a set of inequalities based on what we know. Then we're also going to come up with an objective function that we want to be maximized or minimized. Then once we have all this information, all these inequalities in our objective function, then we graph the inequalities and find out what the coordinates of those corner points are of our shaded region. And then we take each one of those corner points and put them into our objective function, and find out which point is giving us a maximum value and which point is giving us a minimum value. So let's look at one last example here. Let's say that on a flight between Vancouver and Winnipeg, there's business seats and there's economy seats. And when the plane's full, the airplane can hold no more than 145 passengers. And here's some other constraints we have. No fewer than 130 economy seats are sold and no more than 8 business class seats are sold. And we know that the airline is charging $615 for a business class seat and $245 for an economy seat. And the question for the airline is, what combination of business and economy seats would give us the maximum revenue, and what would that maximum revenue be? So we'll start, first of all, by step one was to come up with the constraints in our function. So what we should really do is define our variables first. So we are talking about what combination of business and economy seats. So why don't we say B is the number of business seats and E is the number of economy seats. So the airplane can hold no more than 145 passengers, so the business seats plus the economy seats must be less than or equal to 145. There's our first constraint. And no fewer than 130 economy seats are sold. So that means the number of economy seats must be greater than or equal to 130, because there can't be less than 130. And no more than 8 business class. So the most there can be of the business class is 8. So these would be our constraints. Now, in a lot of word problems, this one included, often we're going to have greater than or equal to 0, because it doesn't make sense to have negative business seats, and it doesn't make sense to have negative economy seats. So often our variables are going to be B greater than or equal to 0, E greater than or equal to 0. And our objective function then would be our total revenue, how much money we get in, and that's $615 for every business seat and $245 for every economy seat. So there's our objective function. Now we have to graph this thing. Now what's a little bit different in this one is we have some very big numbers here. So we could graph this, get a graph out, and it would look something like this. And we could graph it, and we might have E on this axis and B down here, and so then this one here we'd have to do a little bit of work. We'd have to say E is actually less than or equal to, bring the B to the other side. Oops, missed the one there. We get E is less than or equal to, rats, no, I missed the negative sign. Negative B plus 145. Negative B plus 145. So we have this one to put in, this one to put on the graph, and this one to put on the graph. And then these two as well, but they're kind of covered when we just draw this axis here. But yeah, these are big numbers, so it'd be difficult. We could do it, but it'd be difficult to put that on here. So sometimes we might want to make use of graphing technology. And so I've popped up the calculator here. And I'm going to actually enter these in. So graph, I'm going to graph them. And my first one I'm going to put in here is E is less than or equal to negative B plus 145. So this the graphing calculator always just going to have Y or X, but we understand that Y is really E, the number of economy seats, and X is really going to be B, which is the number of business class seats. So I'm going to enter this in here. And then my other equation I'm going to put in there is E is greater than 130. So E is my Y value. So E my y value. So E 130. And then this one's going to be a bit of a problem because this is an x less than or equal to 8. And I only have y values here. The other problem we've got, we'll deal with that in a sec. The other problem we've got is we've got equals to, and we want, in this one we want less than or equal to. So I'm going to go change the type here to, over the arrow, to here. Y is less than or equal to. So I'm going to hit F4 in there, and notice how this is changed to less than or equal to. Whoops, don't want to draw quite yet. And this one here, I want to be y is greater than 130. So I go in here and change the type to y is greater than 130. Okay, let's, I don't know what happened with my calculator there. I had to close it, start it again. So I've put that first one in there. So y is less than or equal to negative x plus 145. So my next one is going to be y is greater than or equal to 13. So I'm going to change the type to greater than or equal to. So it's showing that there, 13. Good. So now we can see when I look at my equations, it should show y is less than or equal to. It's showing that now. I don't know why it was before. And then y2 is greater than or equal to 13. So I've got my two functions in here. I've got this one entered in the calculator, and I've got this one entered in the calculator. Now these three here, what we're going to do with those is we're going to deal with those in the view window. So right now the view window goes from -6 to 6. That's on the x values. But I want and so remember x is b. I want b to go from 0, so greater than or equal to 0, less than or equal to 8. So that's how I'm going to deal with that is I'm just going to do this. I'm going to make my x values go from 0 to 8. And then my y values, so that would mean I would dealt with this one because x is greater than or equal to 0, x is less than or equal to 8. And then e is my y values, and they are greater than or equal to 0. So I'm going to put 0 in there, and I know that the y-intercept of this function is 145, so I'm just going to go to 150. And maybe I'll go up by 10s on there. And now I'm ready to draw this thing. And so I get a picture that looks like this. And now we've got to figure out these regions here. So this is where this g-solve is going to come in. And on this one, I'm going to find some y-intercepts. Why don't we just sketch this here for a sec? So this is kind of what our graph looks like. I've just sketched it there. Here, I'll just so there is a gap underneath here because this line is at 13. So this is the line y equals 13, and this is the equation here. Y is less than or equal to negative b plus 145. So we know that this point here is at 145, and this point's at 13. What we would really like to find is this point and this point. So here's what we know. We know that this is 8 because that's the maximum that x can be. So we know here that x is 8. This must be the point 8, 13 then, because y is 13 along this line. But this one here, we don't know what that is. We're not too sure what that y value is. It's on this line, so we can easily figure that out because we just put 8 in for x, and we get y is less than or equal to negative 8 plus 145. Oops, let's write that again. We're just going to use this as an equation. So y is negative 8 plus 145. So we get y equals 137. So we get 137 up there in that corner. So here's here's our 4 points. Another way we could do this is we could go to gsolve, and we could find a y calculation, so f1, and then on this function, yes, so hit enter, and then it says enter your x value. Well, we want to know what the y is when x is 8, and it'll calculate it for us. See that? 137. So this was our region, and now we know this is the point 8, 137. This would be the point 8, 13. This corner here would be the point 0, 13, and this point here would be the point 0, 145. So here's our objective function right here. So point 1 is the point 0, 145. So if we put in the calculator 615 times 0 is not going to give us anything, but 245 times 145 will. It gives us 35,525. All right, so that's how much money we would make if we went with 0 business class and 145 economy class. Let's do the next one. So that's 8, 137. So we're going to maximize our business class. Let's see. So 615 times 8 plus 245 times E, which is 137, 38,485. So that's a better deal yet. And then we would try this one. Well, obviously this is not going to produce very much money. 8 business class seats, but only 13 economy seats. Not going to make much money here. $8,105. And then obviously 0.4 would give us 0, which would be our minimum. But we want to maximize revenue, so we have found right now, right here, we could answer this question: what combinations of business and economy seats would result in the maximum revenue? We could write down we should have 8 business class seats and 137 economy seats. And what will the maximum revenue be? The maximum revenue will be $38,485. So there's how we can use the systems of inequalities with an objective function to find out maximum or minimum values.